Okay, we're going to do problem 100 with some trees, two binary trees. So, given two roots of two binary trees, P and Q, write a function to check if they are the same or not. Two binary trees are considered the same if they are structurally identical, and the nodes have the same value. So, we've got 2 on the left tree node, and the root node there's 1, right there's 3, and then the same is over here. We can see that it's represented in uh, tree form in here. They're exactly the same. They don't have a left or right piece. It's false. And then if the nodes are not matching for each branch, it is also false. So these mirror each other, but they don't. They aren't the same. So binary trees are typically recursive in nature. So we're going to write some recursion. I was a little bit scared at first with recursion. But as soon as you define a base case and what you're trying to go for, you can kind of let recursion go on its own. Kind of explain as the code goes on. But we're just going to essentially establish our base cases first. So base case is if there are no branches on each of the end nodes, meaning they're a leaf node. So if there is no P and there is no Q, then we found the end and we can return true, provided that they don't satisfy the other following cases as well. So if there's a left or right node on the tree from the leaf node, but there's no left or right the other side, then that means it's false. Then we'll return false. So if there's not a leaf node here, or if there's not a leaf node here, that means that it's unbalanced and it's probably not going to be the same. So we're going to do else if the P node or Q node is not there, then we'll return false. So we're going to have another piece here that asks whether or not the branches are the same. So if this branch is not the same as this branch, then it's going to return false. So we'll do that check here. If the P dot value, and reminder, this value is found when creating a tree node here, value. So we can extract that value there. So if the P dot value is not equal to the Q dot value, oops, that is not how you write a JavaScript function. Then we'll return false because those leaf nodes are not the same. So those are our base cases. As long as those are satisfied, we'll go ahead and return true. So as far as if those are not true the first time around, essentially these are the base cases that will be conditional upon the end, meaning when the stack reaches the end, these will start to jump out and establish true or false or whatever your recursive algorithm says. But we do need to return a statement outside of those conditional statements, which will be our recursive step. So what we'll do is we're going to traverse the trees on from each branch. So from the root node, we're going to go to the left and the right. So we'll go here, P dot left, and Q dot left, sorry. And we'll also return is same tree of P dot right and q.write, which is extracted from here. Essentially what we're doing, and you can see this, the first time around, it's going to be the root node. So P and Q, root node, 1 and 1. So if it's not P and not Q, which means if it's null, then it'll return true. So obviously it's not null, so skip that. If there's not a P or not a Q, then it'll return false. There is a P and a Q, which is this node and this node, or this tree and this tree representative. And then we'll dive into this. If the P.value is not equal to the Q.value, then we'll return false. These are obviously equal, so we'll continue, and then we'll return this recursive statement, which says is same tree, which means that you're going to jump into another iteration of the function, as well as jump in another iteration of the function. So we're now comparing the left and the left of each of those trees. So left and left, obviously they're the same, so we'll continue. But since there's no leaf node after that, then we'll return true on that one. However, if this was not true, meaning if there was, no leaves here, and it was not the same, then we would return false on either of those conditions. So since they're both the same, both of these will return, and the same goes for deeper and deeper trees. So let's go try this and make sure it works. And it is accepted. We'll submit it. And it does great. So since you're only going through once, so each node of the tree is being accessed once, this is an O of n operation, which is as efficient as you can really get. So there we go.